Ladies and gentlemen, hello and welcome. This is 2 Pi R Squared team. My name is Mahmoud Ali. We are a group of students, 34-MET GC students, and this video is a demonstration for our digital system and design project. One day we were playing piano tiles, just like any other one in his free time playing piano tiles, and we were angry that we couldn't get any high scores. So we have decided to build a machine, or as we can say, we want to build a robot that plays piano tiles. And if you want to make a robot that plays piano tiles, you must first know how a capacitive touch screen works. And this is what I'm going to illustrate now. Imagine that we have a touch screen for any device that you have, your iPad, your iPhone, or whatever device you are using that has a touch screen. A touch screen concept is that it is a capacitive touch screen, which means that it has many electrons in the screen itself. All it just needs is your touch. But how does it work? In fact, when you press with your finger on the screen, you close a circuit, an open circuit, an already open circuit. You close the circuit by making a tiny charge transferring from the touch screen to your finger, which makes a voltage drop. And since this all screen have many sensors that detects where the voltage drop happened, it could easily know where your touch has happened. And by this, it could make your functionality very well. For example, if you'd like to open the settings app on this phone, all you have to do is just tap. And this, we created a voltage drop, and the sensors knew that we have made the touch in this specific area above the settings application, so it opens the settings application. Now, moving to the next levels, my colleagues will start illustrating the parts, the specific and details parts about our project. Starting by Sam Fauzi.
And now I'll explain how the data is transmitted from the LDR sensors to the FPGA board. First, the LDR job is to recognize the white tiles from the black tiles. When a white tile comes, its resistance decreases and the voltage increase, and it passes this information to the ADC converter. We need the ADC converter because the LDR sensor's output is analog signal, and the FPGA deals only with digital signals. So we need the ADC converter to change the analog signal from the LDR to the FPGA. The inputs of the LDR from here in the breadboard through this white wire here, and the ADC is an 8-channel ADC converter, but we use only the 4 because we have 4 LDRs only. The data is transmitted through these 8 wires to the FPGA board, and we have the 3 selection lines, A, B, and C. A, B, and C are outputs from the FPGA board. We control which LDR we want to read its data now. And we have output clock for the ADC from the FPGA board, and we have output pulse for start the conversion, and output pulse for the ALE address latch enable to inform the ADC that we want to change the address of the selected LDR.
Hello, my name is Omar Sami. I will now discuss how we simulated the touch using the coins from the hardware side of things. First, when the LDR detects a black tile, it sends a signal through the ADC to the FPGA, which runs the code, and when it decides that it needs to activate a transistor, an enable signal is sent to the transistors. The transistor will then connect the ground to the relay, and the relay will then allow the power to transfer through the cables to the coin. The coin then simulates a voltage drop on the screen, and because it's a capacitive touch screen, the screen treats this voltage drop the same way it treats a touch, as if someone just touched the screen. We used a transistor because when we tried to do it without one, the pins on the board did not generate enough current to activate the relay. But they did generate enough to activate a transistor. So we had to just attach one, and we did this for all 4 relays, and now it just works perfectly.
This is Mazen Magdi. We're going to be talking about the code and the logic behind our DSD project. First off, we started with the ADC clock, which is basically converting the FPGA clock, which is 50 megahertz, to the ADC, which is the analog to digital converter clock of 500 kilohertz. As you can see, we have a counter. It decrements. The counter starts at 249. It keeps decrementing until it reaches 0. Then we send a positive clock edge to the ADC, which inverts the clock. Then we'll talk about the ADC pulse. Mazen, please explain.
So here in the ADC pulse, it's just the same logic as the ADC clock. We have a counter. It starts at 6,000. We have been experimenting a lot with the counter, and we have been trying a lot of values, and this is the value where we feel it's the best. We keep decrementing the counter, and once it reaches 0, we get it back to its original value. So we can keep doing that as long as the program is running. And then, so the pulse clock is used, it's actually needed for the ADC, so that the ADC can, in the pulse width, be able to change the address lines and at the same time read input from the LDRs. Now we're going to talk about the module that handles the main logic. We have decided to write this in a finite state machine. We have been advised that this is easier and better. We have 5 states. In state 0, we start by checking on the selection lines and just toggling between them. So we have, as you can see here, we have 4 LDRs. So basically, we need 2 selection lines. So we keep checking on the selection lines. We check if it's 0, 0, then we need to go to the next one, which is 0, 1, and so on. So we can always keep reading input from the 3 LDRs. We have also other states that Ali is going to discuss.
The next 4 states, states 1 through 4. These are to activate the ALE, which is the address enable, and the start. The ALE is activated first, so we can tell the ADC and the FPGA that we're going to change the address. Second, we're going to start. That means it's going to start the conversion from analog to digital, and it's going to start sending the data from the ADC to the data lines to reach the FPGA. Afterwards, in the next 2 states, we're going to set them to 0, and we're going to set the ALE to 0 and the start to 0 in state 3 and 4. So that we can, when we repeat or when we loop on all the states, we can activate them again, and we don't need to load to change the address anymore or to load the data anymore. So we set them to 0. The last state, Mazen, please explain it.
As Hassam said before, we in the LDR modules over here, he said that there are 8 channels. So any value that a single LDR reads can be expressed in 8 bits. And technically, all these LDRs share the same 8 channels. So at any point in time, one LDR has to be working, as in we have to read an input from one LDR. So here in the module, we first start by, this is the last state, state 5. We first start by checking checking on the selection line, so we can tell which LDR is currently working or is currently selected. After that, we start checking on the input, which basically represents the value of the light intensity currently that the LDR is reading. After we check on this value, we check if it's lower or greater than a certain threshold. And as you can see here, we first start once we check on the threshold. We start by clearing or setting the LED, which is just basically for debugging purposes. And the most important part is we set the output pin. The output pin is over here right on the board. We have 4 output pins, each for a relay. Or a transistor, actually, to be more precise. This output pin, when activated, it sends an enable signal or a voltage signal to the breadboard over here, which then activates one of the relays depending on which LDR was activated, and hence giving voltage signal to the coin, which then simulates the touch. And actually, just to wrap this up, at the end we have to get back to the first state so we can keep looping on and on.
My name is Ahmed Tariq, and I'm going to describe the main module, which has all the other modules which were described by Mazen and Ali. First, we have some inputs and outputs, starting with output X, which is the ADC clock, this one, and then we have the ALE and start, which are this gray one and this purple one, and then we have the 4 outputs, starting from the black one to the other black one, this one, and then we have the three selection lines, and then we have the 8 inputs. Then we have the ADC clock, which inputs the ball clock and output the X. Then we have another ADC pulse, which inputs the ball clock and output Y, which is passed to the FSM. And then we pass everything to the FSM module, which was described by Ali and Mazen. First we pass the ABC, which are the selection lines, and the address enable, then the start, and the 4 LED which were used for debugging, and for outputs, and finally we have the wire Y and the input in.
Hello again. Now we have knew all the details about the project, but a tiny detail we didn't talk about. How actually we could create a voltage drop on the touch screen. We have replaced our fingers with the coins, just like this one. We used the copper coins because all we know is that copper is the best conductor for electricity, so that when the FPGA sends a signal to the relays, any of which relays which has a corresponding LDR module that knows that a black tile has been detected, it sends a signal to that relay and connects this wire to the ground, which touches the copper coin, which makes the voltage drop on the iPad, and this makes the touch. Now we know every detail about the project, or in other words, you can make yourself a new robot that plays piano tiles and make a new high score, and even beat your friends. At the end, I'd like to thank our TAs Yasmin and Omar for helping us very much in this project, and special thanks for Dr. Muhammad Al-Mahdi for letting us do this project under his supervision. Thank you very much guys for your time, and I hope you find this video good and helpful. And now I'll just let you see how the robot works and make a new high score in piano tiles.
I'm running away from this pain. I'm trying to find a new way where the sun's shining down on my face. I'm running away. You're in a toxic relationship. Time to be free. my face. I'm running away. You're in a toxic relationship.